Let's crack management exams. Join Unacademy, India's largest learning platform, and get the best possible resources to crack the CAT, the GMAT, and all other management exams. My name is Anand Venkatesan, and I'm an educator with Unacademy. Here's a brief look at my profile. As you can see, I've done my engineering from VIT Vellore and then went on to do my postgrad from IIM Bangalore. I have experience of having worked in the FMCG sector and also have almost a decade's worth of experience in having trained students through a variety of management exams. I teach the quant and the verbal sections. Here's a quick look at what Unacademy gives you, what you can avail of on the Unacademy app. It's actually one of the best apps to start learning, because what you get is four distinct things that you get. Live classes. You can attend classes by educators live from the comfort of your home, and these happen, you'll have multiple options on any given day of the year, right? Number two, you get live tests and quizzes, which means that whatever you learn in class, you can then apply it yourself by practicing these tests. Number three, you get structure. I think one of the most useful things is how much time do I spend on a particular topic, how much practice should I devote to it, how much depth do I need to get into, how do I keep regular throughout the course. All of these difficulties that students face are solved if you join a batch, right? And the advantage of joining a batch is that your preparation is, journey is sort of regularized. You have fixed number of days in which you have classes, and then the rest of the time you can devote for your practice. And educators will also handhold you through revision, through practice, and also the depth that is needed. And remember, I think the big advantage on all of these points is that there's absolutely unlimited access once you subscribe on the platform. Any number of sessions you can attend, any number of batches you can join. You can take mock tests and quizzes unlimited number of times. There's absolutely no upper limit to this, right? Quickly sort of talking about each of those. Educators, I think one of the biggest differentiator, one of the biggest needs for training is to learn from the best of educators. You can see Unacademy has some of the top educators in the country, people who are subject matter experts, people who've scored 99 percentile, whether overall or sectional, and also people who have experience teaching online, right? Number of minutes that they've clocked online tells you that these are people who understand the online medium. Classes that educators take are of two types on the platform, on the app. One is called the special classes and the other one is called plus. Well, the difference, quite frankly, is that special classes are free of cost, which means that once you register on the app, you can take these special classes as trial sessions, right? Experience how the platform works and so on and so forth. Plus, on the other hand, you can only access if you subscribe, right? But the big advantage with plus is that you get access to many batches, right? And like I said, batches come with the distinct advantage of structure, but also that there are many more live classes once you are a plus student, right? You can see the kind of batches that I'm talking about. You can choose batches which are either targeting the exam and it's like a basic course, or closer to the exam there are a lot of crash courses or practice courses that get launched. So instead of working on the basic concepts, maybe I want revision, right? So that also happens. And then you also have these micro courses, specific topics, and then capsule courses either on arithmetic, number systems, algebra, parajumbles, data sets, etc. A quick word on some of the new batches that are coming up. Come December 21st, this is a batch that is beginning. It's called a beginner's batch. It's a basic batch for learners starting on December 21st. Three very talented smart educators will be launching this batch. Remember, you get a 10% discount on all of these batches that I'm going to talk about by using my referral code. You can see that I've highlighted at the bottom. That's AV01. Okay, the second batch that I'm telling you about is the CMAT batch. CMAT 2021 is coming up. So there's a revision batch that we've launched, that we're launching on coming 21st of December. And the third batch is a complete weekday batch. I think it's also one of the most exciting batches, which begins on the 23rd of December. All of these three batches that I mentioned, you can join. And make sure that you join these courses. As you can see, Mr. Arun Sharma is a household name in the world of CAT preparation, and he's going to be leading this batch. So, what are you waiting for? Just join, Unacademy, get yourself a subscription channel, and join this batch. And remember to use my referral code AB01 because that gives you a 10% discount. When you are subscribing, these are the kind of plans you will see, right? My suggestion, if your exam is 3 months away, choose a 6-month plan. If your exam is a year away, choose a 2-year plan. Basically, choose the longer term plan because that gives you access to the educators, not just for the written test, but also for interview preparation. Alright, here's the agenda for today. We're going to discuss number properties. In a previous couple of sessions, we've already discussed the basics of number properties, number classification, LCM, HCF, and in fact factors and multiples as well. So today we're going to take the discussion forward, discuss some other topics slightly advanced in level. Even insofar as the GMAT goes, some of these questions are going to be fairly rare. What do we learn? Well, we'll talk about the last digits of a number, specifically the units digit, which is more important. And probably in today's topic, it's going to be more relevant in the GMAT exam. But then we'll also look at some other shortcuts and discuss remainders, how to deal with remainders, and all of this we will obviously fortify by practicing loads of questions on the same topic. All right, let's start with the first question, the first topic, which is called cyclicity, right? Which deals with the last digit of a number, in fact last digit of a product, right? Now the concept of concept of cyclicity or last digits is that when you are multiplying, adding, subtracting, when you're performing an arithmetic operation on numbers, then their last digits will also go through these very operations, right? And I think the theorem is that the logic or the basic idea is that if you want the last digit of the answer, then you should focus your attention on the last digits of the individual numbers that are being added, multiplied, subtracted, and so on, right? So, but when you're dealing with a product or an expression that is fairly easy to determine, isn't it? So let me take an example first. Say that we consider the product 273 into 592 minus 628 into 37, right? Let's say we want the last digit of this product, right? So the logic here is that if I'm multiplying the last digits, if I'm multiplying these numbers and I want only the last digit, then in every arithmetic operation only include the last digits themselves, right? Can you see what I've done, right? I have only counted, I've only singled out the last digits within this expression, and that's something I'll calculate. 3 into 2 is 6 and 8 into 7 is 56. Again, don't bother with the previous digit, just write the last digit. 6 minus 6 will in fact be 0. So what I can conclude from here is that if this is the expression whose last digit I want, then the last digit would be 0, right? So it's a fairly easy concept. If you're multiplying, subtracting or adding, then just zero in on the last digit and then perform the same arithmetic operations on them, right? In fact, on a related note, there is also a concept called the digit sum, right? There is this concept called digit sum, right? Which sometimes can be a useful concept, and in fact it's a concept which has a very practical application, which is in the world of numerology. I'm sure you guys have come across people who talk about numbers that come about when you add digits in the date of birth, for example, or even time of birth, and essentially digit sum is that concept which figures out the sum of all the digits of a number, but digit sum will always be between 0 and 10. Right? It has to be a single digit value. It cannot be a two digit sum. What do I mean? So supposing we want the digit sum of 273, right? Which means if you add 2 plus 7 plus 3, what happens? 2 plus 7, 9, 9 plus 3 is 12. But that's not a That's not a single digit number. So you come back to 12 and you do this process all over again. 2 plus 1 is 3. So this is called the digit sum. Right? So digit sum will be a single digit that denotes the sum of all the digits that make up a number. Right? That's called the digit sum. Right? Now digit sum, and digit sum is something which is which is quite prevalent in the field of numerology, because that's what you'd do. You'd keep on reducing the sum to a single digit value. Now why am I talking about digit sum? Is there because there is an interesting property of the digit sum, right? And here is the interesting property. The property is that the digit sum of a number n will be the same as the remainder when n is divided by, what do you think? N is divided by the number 9. Right? So for example, 273. Right? We know that the digit sum was 3. We just calculated that. Right? So if the digit sum is 3, we can also quickly check what happens if you divide this number by 9. 9 3s are 27, and then 3 comes, 9 zeros are 0. 9 into 30 is 270. And indeed the remainder is 3. Yeah? So just a useful sort of inference, useful sort of rule here, which is that all you need to do is add the sum of divide the number by 9, and whatever you get as remainder would be the digit sum. So for example, if I say how many numbers, answer this question, right? How many 4-digit numbers have a digit sum of 5? Answer in the chat. What do you get as the answer? Right? How many 4-digit numbers have a digit sum of 5? What do you think? Okay, I can see that Shaurya has an answer for me. Let's see if you're right. Right, just give me a second, Shaurya. Right, let's figure this out. What does the question say? Um, how many numbers have a digit sum of 5? Which means how many numbers give a remainder of 5 with 9, right? And that immediately should translate into how many numbers are of the form n is equal to 9a plus 5, right? Dividend equal to divisor into quotient plus the remainder, right? So basically, instead of counting the values of n, you'll count the possible values of a, right? So smallest value of a, which makes a 4-digit number, right? So you want to reach 1000, right? So if you divide 1000 by 9, what do you get, right? You'd get 111, right? 111 into 9 would be 999 plus 5 would make it 1000. So the smallest value of a will be 111, and the largest value of a, if I make it 1111, it will exceed. So I'll get 1110, right? Hit and trial tells me these will be the minimum maximum values. So the possibilities are b minus a plus 1. So 1110 minus 111 plus 1. Indeed, the answer is there are 1000 such numbers. Good answer, Shaurya. Right. So getting into the actual topic, right? It's good to know about the way last digits and digit sums work, but how about the last digit of an exponent, right? How about the last digit of a number raised to another power, right? How do you deal with those problems? Well, the concept is the same, right? That the last digit will depend on the last digit, but in this case, the exponent's last digit will depend on the last digit of its base, but more importantly, it runs in a cycle, it repeats, right? Which means it can only take a fixed number of values and then it comes back and it runs in that cycle all over again. And that cycle that we're talking about is called its cyclicity, right? So for example, if I consider this exponent 182 to the power of 17, this denotes 182 multiplied with itself 17 times, right? But if I'm interested in the last digit, then I will say that the last digit of this number, of this exponent, would actually be 2 times 2 times itself multiplied with itself some 17 number of times, right? So how do I calculate that? And secondly, even if I can calculate the last digit of 2 to the power 17, how do I make it scalable? How do I calculate it for a power which is even higher, right? So in this case, you try and work that out. You do a little bit of it and trial. What you do is that if you know the concept of cyclicity, then you will know that it repeats after a certain number of values, right? So why not work with it one at a time and see when it starts to repeat, right? So to find cyclicity, what you do, for the cyclicity of the digit 2, for example, right, you multiply with itself till we find a repetition, right? 2 to the power 1, 2. Then 2 into 2, that gives me 4. Then multiply 4 with 2, right? Remember, I want 2 cube, but 2 cube itself would be 2 square into 2, and I know that 2 square ends in 4. So instead of considering them as powers, you keep multiplying the previous last digit with, with 2. So 2 into 2, 4, 4 into 2, 8, and then 8 into 2 will be 16, which ends in 6. But then what happens if you multiply 6 with 2, right? 6 2s are 12. So it comes back to 2. And now you can see that these are the only 4 values that will form the cycle, because after that, since you get 2 all over again, it will again go from 2 to 4 and then to 8 and then back to 6. And then the cycle repeats again and again, right? So what you've seen here is that the digit 2 has a cycle of 4 digits, 2, 4, 8 and 6. And these are the only 4 possibilities for the last digit of 2. Some 2 raised to the power, some power. But then so far, remember, we haven't considered the power at all, right? Now, how do I use cyclicity? How do I use it? How do I use the fact that there are only 4 digits that an exponent with base 2 can take, right? Well, what you do is that you consider the power now, and then you divide that power by the cyclicity, right? Essentially, the quotient of that division will tell me how many cycles, how many complete cycles will be there. So for example, the number that I took was 182 to the power of 17, sorry. Now, what this means is that the direction is that you take the number 17 and then you divide it by the cyclicity, which is 4. And what happens? 4 4s are 16 and the remainder is 1, right? So what does this 4 tell me? That the cycle of 2486 will happen 4 times, right? So 2486, then 2486, then 2486, before finally, once I've finished 4 cycles of 2, 4, 8 and 6, right, I'm left with the remainder, which is one more time 2 will come, right, which means this is where I finish, right. After 17 occurrences, you'll get these 17 last digits, and the 17th digit will in fact be 2, right. So that's the last digit, right. So first you find out the cyclicity. Number 2, you divide the power of the exponent with its cyclicity and find out the remainder. Then you take that remainder and say that denotes the digit from the cycle, right. So if I get a remainder of 1, choose the first digit in the cycle. If I get a remainder of 2, choose the second digit. If I got a remainder of 3, then you choose the third digit in that cycle. And if you're dividing it by 4, you can't get remainder as 4. So if you get a remainder as 0, then you will choose the fourth digit in that cycle, right. And so I hope that it makes sense to you, right. So after determining cyclicity, divide 17 by 4, and the quotient of 4 tells me that there will be 4 powers of 2, 2 power 4, 2 power 4, 2 power 4, 2 power 4, which in a sense is saying the cycle repeats 4 times, and then at the end of it you're left with one digit, so the last digit will be 2, right. But obviously the way you apply it in exams, I'd rather that you know the cycle and then calculate the remainder and say, okay, that digit in the cycle, right. And remember, this is something that you can do with any digit, right. The logic is that every single digit in the number system, in the decimal system that we use, we have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7 and 8, as well as 9, right. And these 10 digits will each have a cyclicity that might be different from the other ones. So you can see that 0, 1, 5 and 6 in the table have been shown to have a cyclicity of 1. What does that mean? It means that the last digit will always remain the same, right. A cyclicity of 1 tells you that the last digit will not change, it will remain itself. So if I take 25 to the power 500, it doesn't matter what the power is, 25 to the power something will always end in 5, right. So that's one cyclicity. The second cyclicity is 2, right, and there are only 2 digits which have a cycle of 2. These are the numbers 4 and 9. Think about it, 4 square. So if I write the cycle for 4, I'll write it as 4, and then 4 into 4, 16, that's 6, and then 6 into 4, 24, that's again 4, and then 4 into 4, 16, that's again 6, and then 6 into 4, 24, again 4, and you can see 4, 6, 4, 6, 4, 6, 4, 6, that's a cycle of 2 digits, right. 9 also has a cycle of 2 digits, 9 nines are 81, 9 ones are 9, right. There you go, this is the 2 digit cycle for 9. It will either end in 9 or it will end in 1, there is no other possibility. And then comes this group of digits, right, 2, 3, 7 and 8, right. These are 4 digits that repeat in a cycle of 4 digits, and you can easily generate these, right. For 2 we've already seen that the cycle is 2, 4, 8 and 6. How about 3? So I can write 3, then multiply it with itself, 3 into 3, 9, multiply 3 with 9, 9 3s are 27, 7, 7 3s are 21, 1, and then 1 3s are back to 3. So with 7 7s are 49, 7 9s are 63, 7 3s are 21, 7 1s are 7. And finally 8 8s are 64, 8 4s are 32, 8 2s are 16, 8 6s are 48. Right? So the idea is that 2, 3, 7 and 8 are 4 digits which will repeat in a cycle of 4 digits. There are obviously digits which repeat in a shorter cycle of 2 digits, or maybe don't repeat, repeat all the time, also accounted for, right. Okay, so that's how you use the cyclicity. Remember, a quick look at the cyclicities. 1, 2 and 4 have an LCM of 4, right. 1, 2 and 4 have an LCM of 4, and the other thing you should remember is that when you take the power and you divide by the last digit of the cyclicity, then what if the power is of the form 4k plus 1? Now why 4k plus 1? Well, it turns out that 4 is the LCM of these 3 digits, right. So any multiple of 4 will be a common multiple of the cyclicities 1, 2 and 4, right. So if the power is indeed a multiple of 4, and remember, if you look at the cyclicities, right, if you write the cyclicity for 2, for example, 2, 4, 8, 6, Cyclicity for 3 will be 3, 9, 7, 1. Right? Cyclicity for 7 will be 7 7s are 49, 7 9s are 63, 7 3s are 21, 7 1s are 7. Right? So you can see that the first digit is always the digit itself. Right? So if a number has a cyclicity of 1, then it will mean that the last digit does not change. Right? Okay, let's try and apply this on some questions. Right? Here's question number 1. And the last digit of n equals 3. What about the last digit of this expression, this product? Let me know in the chat what you get as the answer. Impatience already manifesting itself. Okay, sorry, say 6. Let's see. Right, since last digit of n is 3, the last digit of n plus 1 will be 4. N plus 3 will be 3 plus 3 6. N plus 4 will end in 7. N plus 5 will end in 8. And n plus 6 will end in 9. Right? So you want to multiply these digits and find out last. So again, what I can do is I can multiply them in pairs. Right? 4 into 6 is 24, which ends in 4. 7 into 8 is 56, which ends in 6. So it becomes 4 into 6 and 9. And then 4 into 6 is 24, that ends in 4. So it becomes 4 into 9, which is 36, that ends in 6. So the last digit of the number would be 6, absolutely. Yeah, I'm just going to be back in a second. Sorry. One, okay, right? So it's like a tricky way of asking you this question, right? Because it says the rightmost, which is obviously the units digit, but it asks you for the rightmost non-zero digit, which means ignore all the zeros that come, and then what is the digit that comes before them, right? So basically I can write this exponent as 3 power 2720 into 10 power 2720, right? This will be a bunch of zeros, in fact 2730 zeros, so ignore that. So we want the last digit of this number, right? So first work with 3 and figure out the cyclicity of 3. 3 into 3 is 9, 3 into 9 is 27, 3 into 7 is 21, and then 3 into 1 comes back to 3. This tells me that the cycle of the digit 3 will be 4 digits. So what do? I take the power and you divide this by the cycle, right? So next step, so this was step number 1, right? Next we come to step number 2. right? Step 2 says take the power and divide this by the cyclicity, right? Now you don't really need to divide because you know the last two digits are divisible by 4, so this number will be perfectly divisible, right? But just to prove a point, let me show you, right? 4 into 80 will be 320. So there you go. Remainder is 0, right? That's step number 2. Find out the remainder, right? How about the last step, step 3? What did we say? You can take the remainder and that will tell you what the last digit in the cycle will be, right? So remainder of 0 implies that it will be the last digit of the cycle, right? So go write the cycle down. 3, 9, 7 and 1 means the last digit will be 1. So last digit we want for the expression given, last digit would be equal to 1. Okay, how about this one? Should be fairly easy. Let's see if you can do it mentally in 30 seconds. Yeah, absolutely, because you already know that the last digit of 3, the cycle of 3 is 3, 9, 7, 1, right? The question is which one. So divide 59 by 3, sorry, by 4 and you'll get 4 into 14 is 56. You'll get the remainder as 3. So third digit in the cycle, answer 7. Okay, how about the fourth one? Okay, let's see if that's right, Shaurya. Right, so here, I mean, ignore all other digits, just focus on the last digit. So here you have 6, a power of 6 will always end in 6, no problem, right? A power of 4 will end either in 4 or 9, right? Then if the remainder is 1, it would be 4. If the remainder is 9, then it would be, sorry, if the remainder is 0, then the last digit would be 9. So here, the power of this exponent 892 is divisible by 2. The cyclicity is 2, right? So if you divide the power by 2, you get remainder as 0. If the remainder is 0, then last digit would be, sorry, 4 or 6. So here the last digit is 6 into 488 to the power of, sorry, 8 to the power 534. Now the cycle of 8 is 8, 8 8s are 64, 8 4s are 32, 8 2s are 16 and then back to 8. So this is the cycle of the digit 8. Now take the power 534, in fact forget 534 divided by 4, instead do 34 divided by 4 because you are bound to get the same remainder, right? This tells me that the remainder is 2. right? So you want, since the remainder came out to be 2, second digit in that cycle is 4, right? 6 into 6, 36, 6 into 4, 24, last digit 4, right? So indeed, correct answer, Shaurya. Here's the fifth one. Right, let's figure out. Uh, Can you tell me how you got this answer, Shaurya? Because you want the fourth root, right? You want basically 38416. Fourth root of that, right? I don't know. There's a method to calculate the fourth root, right? Clearly isn't. So obviously you don't try to calculate the fourth root. You instead think if this is x, then 38416 would be equal to x to the power 4. So the fourth root of one of these 5 choices should be 38416. In fact, by using the last digit logic, you will say whatever is the last digit, if you raise it to the 4th power, it should become 6. Right? So obviously what you can straight away rule out is anything ending in 1 will only end in 1. Right? And what about 3? 3 into 3 is 9. What is the cycle for 3? 3 into 3 into 3 into 3. What do you get? 3 into 3 is 9. This is also 9. 9 into 9 will get me 81. Right? So this also goes away. 15 always ends in 5. Right? 15 into 15. If I do 5 into 5, it will always come out to be 5. Right? So 5 to the power 4 will end in 5. So that's ruled out. How about 2? So if I do 12 to the power 4, that's going to be 2 into 2 into 2 into 2. Right? 4 times 4, that's 16, 6. Okay, so 12 to the power 4 is possible. How about 14 to the power 4? That's 4 into 4 into 4 into 4. 4 into 4 is 16, 6. 4 into 4 is again 6. 6 into 6 again ends in 6. So it could be one of these two. So how do I choose between 12 or 14? Yeah. Well, at this point you could probably multiply. Right? At this point you could probably multiply and check it out. Right? So for example, 12 square is 144. If you multiply 144 with itself, it will give you a fairly good idea, right? 14 square, in fact, 140 square, 14 square is 196. So 140 square will be 19,600 and then a little more than that. So it seems more likely that the answer is option C, 14 to the power 4, right? Because 114 square is 140 square is only in the 19,000s. So there's no chance that it will reach 38,000. So you're better off picking the other choice. Alright, here's another one. About the last two digits. Oops. Yeah, it sounds tricky, right? How do you get the last two digits? Right? All we've been talking about was the last digit. The last two digits. Where and how do I get the last two digits? Right? Well, it turns out this is like a trick question. I mean, trick question, not that it's easy, but trick question because you can employ a couple of tricks with these kind of exponents, right? Especially 7 and 5. Right? Okay, let me tell you more. So what is 5 to the power 80? You can write this first of all as 5 square, 5 to the power 2 into 40. Right? Let me start with that here. 5 to the power 80 can be written as 5 to the power 2 into 40. Now, if you've done exponents, then you know a power m into n can be written as a power m raised to the power n. Right? So this becomes 25 to the power 40. Okay. Next step, whenever you have a power of 25, know that it will always end in 25. 25 raised to the power a value will always be 25. Right? It's like a magic trick. If you multiply 25 with itself, what is 25 square? 625. Again ends in 25. What is 25 cube? That's like 625 into 25. That's again 25 into 25. It will also end in 25. Right? So trick that we've learned is that 25 to the power n always ends in 2 and 5. Right? Okay. In fact, it turns out that if you have something with 5 in the base, right? If the base contains 5, then it turns out that this number either ends in 25 or 75. Those are the only two possibilities, right? So when is it 25 and when is it 75? It turns out that it will be 25 when, let me call this digit A. So it will be 25 if A into n is even. Yeah, the second last digit multiplied with the power, if one of them is even, then the number will end in 25. If both are odd, then the number will end in 75. So for example, 15 cube, since this is odd and this is also odd, 15 cube will in fact end in 75. You can check it out. 15 square is 225. 225 into 15 will be 3375. Right? So it does end in 75. So that's a trick to remember, that 25 raised to the power something will always end in 25. Similarly with 7 also there is a trick. The trick is that 7 ka power, you can write this. You can remember this as 7 to the power 60 can be written as 7 power 4 into 15. Right? And it turns out 7 power 4 has a special significance, because if you calculate 7 power 4, that's 2401. Right? Which means that the last digit of this number is 1, which means, in fact, the last two digits are 0 and 1. Right? So it turns out that this will always end in 01. 7 power 4 always ends in 01. And the moment I get to 1, life is simple, isn't it? Right? So trick to remember. So my answer, first part of the number, first part of the product ends in 25. The second part ends in, so this is Yeah, this will be into 0, 1. So my answer will be 25. Option A. How'd you get B? Sure, yeah. Right, I'm just going to move on. Here's question number 7. What about this one? If A plus B plus C as the last digit, and A, B and C are 3-digit numbers whose sum ends in 3, then what can you say about the last digit of A power 17 plus B power 37 plus C power 57? Right, indeed. Right, this question uses that property that we've done, right? Whenever you take a number whose power is of the form 4k plus 1, a multiple of 4 plus 1, then the property is that its last digit is unchanged. It doesn't matter what the last digit of the base was, it will remain the same, right? As long as the power is a multiple of 4 plus 1. And you'll notice all three numbers here, all three powers here are in the 4k plus 1 form, right? Which basically will tell me that this expression reduces into last digit of this expression at least will be last digit of A plus last digit of B plus last digit of C, because the power is of the form 4k plus 1. And if it's A plus B plus C, we already know the last digit of A plus B plus C, which is 3. So we can indeed determine this as 3, right? So whenever the power is, a multiple of 4 plus 3, a multiple of 4 plus 1, do remember that its last digit remains unchanged. Right? Alright, so this was a quick look at last digits. The second portion in today's session is to talk about remainders. It's a fairly rare, let's say, to deal with remainders in problems, but I'll quickly sort of give you an overview. The basics of a remainder we've already studied, that this comes about from the division identity, dividend equal to divisor into quotient plus remainder. We can also use the notation R of A to say that this is the remainder when A is divided by a certain divisor, right? R of A means A is the dividend, right? Remainder of A when division is happening with a particular divisor, right? And now I'm going to list out some properties, right? Remainder of A plus B. Right. So if you're trying to divide a number, if you're trying to divide two numbers, right? In fact, you're trying to divide the sum of two numbers and calculate the remainder. So instead of adding and then doing the division, you can also individually divide and add their individual remainders, right? So this first property basically says that a remainder of a sum will be equal to sum of their individual remainders. Basically, for example, if I'm dividing, 59 by 6, and you also divide, let's say, 71 by 6 or let's say 74 by 6, right? And and then I add 74 and 59 and then I divide it by 6, right? What do you think will be the remainder, right? So remainder here will be 6 into 12 is 72. So remainder I'm getting is 2. Here 6 into 9 is 54. Let's take a different number value for now. Actually 69 le lete hain, right? So if it's 69, 6 into 11 is 66. Remainder will be 3. So what happens if you add 74 and 69? Expectation is that it would be the sum of these individual remainders R1 and R2, right? So this should be equal to R1 plus R2, which is equal to 5. Is that true? Check it out. What is the sum of 74 and 69? 143. So if you divide 143 with 6, 2s are 12, 23, 6, 3s are 18. Right? Yes, indeed, remainder is 5. So that's the right answer. Right? So similarly, there are 3 other properties. Remainder of a sum equals sum of remainders. Remainder of a difference equals difference of remainders. Remainder of a product equals product of remainders, and remainder of an exponent will be equal to remainder of the base raised to the nth power. Right? So 4 basic properties which basically say okay, instead of whatever operation you perform on the dividend can also be replicated with the remainders, right? If you're adding the dividends, add the remainders. If you're subtracting the dividends, subtract the dividend. If you're multiplying them, multiply the remainders. If you're calculating remainder of an exponent, just divide the base and raise it to that corresponding power, and that will also give you the same answer, right? But there are a couple of things that you need to keep in mind when you are applying these properties, right? Some sort of points to remember. One, that the remainder must always be a non-negative value, right? It cannot be negative. Remainder cannot be negative, must not, right? But take it with a pinch of salt, because sometimes taking the remainder, considering the remainder as a negative value has its own advantages, right? But you can never say the final answer for a remainder is negative, right? You can't report negative values for a remainder. Intermediate steps, sure, you can consider remainder as negative, right? So one must be non-negative and must also be less than the divisor, right? If you're dividing a number with 7, can't get a number which is remainder which is 7 or more than it, right? It has to be less than 7. So it has to be from 0 to 6, right? So first property. Now the second thing is that if you are applying those 4 rules, if you are adding remainders or subtracting them or multiplying them, there's a chance that the result you get, it exceeds the divisor, right? Since you're adding things, you might sometimes go beyond the divisor. What do you do then? Well, if the remainder becomes, so if the remainder exceeds the divisor, then all you need to do is you divide it again. Right? Consider our previous example. Supposing I was dividing 71 by 6 and then I was separately dividing 59 by 6. Right? What is the remainder I'd get here? 6 into 11 is 66. I'll get the remainder as 5. Right? What is the remainder I'd get here? 6 into 9 is 54. Again I'll get the remainder as 5. So what happens if you divide 71 plus 59 by 6? Right? Now notionally speaking, this is 130, right? And so I know that the remainder I'm supposed to get, 6 2s are 12, 6 1s are 6, remainder is 4, right? But can I use this rule, right? Can I do R1 plus R2 to get the answer? Because R1 plus R2 will in fact be 10, right? So when you know that it exceeds the divisor 6, then you divide 10 by 6. And what do you get? You get the remainder as 4, and that's indeed the correct answer, right? So if you add or multiply and it turns out that the number exceeds the divisor, divide it again. If you're subtracting and you get a negative value, right, then what do? Then you make it positive. How do you make it positive? You can add the divisor to it, right? If it becomes negative, you can feel free to add the divisor. So for example, if and by the way, what does negative remainder in fact mean, right? So consider an example. So for example, if you are dividing 71 by 6, then you get the remainder as 5, right? Which basically says that 71 is 6 into, what was the quotient? 11 plus 5, right? So basically a remainder of 5 means it's 5 more than a multiple, than the 11th multiple of 6, right? So a positive remainder will mean that after a certain multiple you move ahead, So what would a negative remainder mean? After a certain multiple, you don't move ahead, you move back. So if the remainder turns out to be minus 3, what does it mean? It means go to a multiple of 6, but then step three numbers back, right? So here too, instead of calling this remainder as 5, you could also say this is 6 into 12 minus 1, right? So it's the 12th multiple less 1. So minus 1 is the same as plus 5. So these two remainders actually mean the same value, right? So basically what happens if the remainder becomes negative? If you get minus 1 as the remainder, then you can add 6 to it and it will become positive, it will come back to plus 5, right? If the remainder was minus 3, then answer will be minus 3 plus 6. You say, okay, the remainder actual answer is 3. Why? Because you are dividing it by 6, so you can add back the divisor, right? And by the way, this is a very, very common substitution that you do. If you are solving a problem on remainders and you notice that the remainder is 1 less than the divisor, right? It's equal to divisor minus 1. Then it's actually a good practice to write the remainder as minus 1, right? Think about the example that I just took, right? 71 can be written as 6 into 12 minus 1, right? So this basically means remainder of 71 is minus 1, right? So instead of, but if you know the remainder of 71 when divided by 6, you know this as 5, right? So the moment you notice that you get a positive value which is 1 less than the divisor, don't write it as 5, write it as minus 1. It will always be advantageous to write the remainder as minus 1. 1 and minus 1 are comfortable numbers, right? Hope those points are clear. If you have any question, do ask me right away, Shaurya. But for now, if it's all clear, then try to tell me what the answer for this question is going to be. What happens if you divide 7 raised to the power 25 by 8? What would the answer, what would the remainder in fact be? What is the remainder if 7 raised to the power 25 is divided by 8? Obviously not a question you solve by division. So you need to use the property of remainders. Which property will I use here? It's kind of obvious. Remainder of an exponent raised to the power n can be calculated as remainder of just the base and then raising this remainder to the nth power. This is the property that you need to use, right? See if you can figure out how to use it though. There's a bunch of you watching this live. Feel free to jump in and tell me what you think is the answer if you did manage to solve it. And this is the part of math which could be fun potentially. Now remember, don't let this kind of question intimidate you. It doesn't matter what you do, how you solve. You are bound to get the right answer, right? So here's the best method to solve this question, which is to write. Now what happens if you divide? First of all, in this case I'll say the remainder of 7 to the power 25 will in fact be remainder of 7 raised to the power 25, right? And what are we dividing it by? We're dividing it by 8. So if you take 7 and you divide it by 8, clearly 8 zeros are 0, you'll come with the remainder as 7, right? And now you'll notice that, oops, the remainder is actually 1 less than the divisor, right? So why write it as 7? Why not write it as minus 1, right? And does that help me? Indeed it helps me, because minus 1 raised to the power 25 would be minus 1 raised to the power odd value will be negative. If the power were even, then it would be positive. So this turns out to be minus 1. And right in the end, if the remainder is minus 1, what do? I add the divisor back to it so that it becomes positive. So I add 8 to it. This becomes minus 1 plus 8, 7. Right? So 7 to the power 25 when divided by 8 will result in the remainder as 7. Right? You could have also done a ton of other things with this question. Like for example, you could have also written this. You can also have simplified this, broken it down into multiple pieces and solved it also, right? And that wouldn't be entirely wrong, right? So for example, if I had taken this as, so let's say this is 7 into 7 power 24, this can be written as 7 into 7 power 4 raised to the power 6, and I know 7 power 4 is 2401, and when I divide 2401 by 8, 8 3s are 24, I'll get the remainder as 1, right? So this would become, the remainder of 7 is 7, remainder of 2401 is 1, and this would be raised to the 6th power. So it turns out that the answer is still 7. Yeah. You can see that magic happens irrespective of what your approach is. It will result in the same answer. Alright, try this next question. Two numbers A and B when divided by 8 give me remainders of 3 and 4 respectively. What's the remainder when this expression is divided by 8? Question number 9. What do you guys think? By the way, I'm starting a new batch tomorrow, which is a plus batch for CAT 2021 aspirants. Tomorrow we're going to start with number properties in a little more detail. So do join me tomorrow if you know you're interested in that. We start at 10:15 in the morning. Right. So if I want the remainder of this expression, I'm going to use the notation here. Remainder of a cube plus 3a square b square plus 3b cube. Right. Remainder of an expression, which is the sum of three things, will be remainder of those individual things. Okay. And remainder of a cube, in fact, can then be also written as remainder of a whole cube. Right. So, I mean, you don't really need to write this, but you will treat it like this, right? Remainder of 3 into remainder of a the whole square, and then into remainder of b also squared, and then finally add remainder of 3 into remainder of b when squared all over, when cubed in fact, right in the end it's cubed, right? So what happens here, remainder of a is given to me, right? We're already given that remainder when a is divided by 8 is 3, and when b is divided by 8 you get the remainder as 4. So let's substitute remainder of a and remainder b. Remainder of a 3, so 3 cube 27. Remainder of 3, when you're dividing 3 by 8 you would get the same remainder back as 3, right? Remember, you're doing 3 divided by 8. 8 zeros are 0, remainder would be 3. So I'm going to write this as 3. Remainder of a is 3, but whole squaring, this will become into 9. Remainder of b is 4. Squaring that, 4 square is 16, and remainder of 3 is 3, remainder of b is 4, 4 cube is in fact 64, right? Clearly the sum will exceed 8, right? So when you know it exceeds 8, what can I do? I'll divide it all over again, right? So calculate the remainder for each of these values, again dividing it by 8. 8 3s are 24, remainder is 3. Now notice in this product you have 16 which is divisible by 4. Divisible by 8, and so is the number 64 also divisible by 8, which means that somewhere when you divide 3 with 8, you get the remainder as 3. 9 with 8, you get the remainder as 1. But 16 with 8, you get the remainder as 0. And similarly here in the next term, you'll get remainder of 3 is 3, but remainder of 64 is 0. So what happens? Product becomes, these two products become 0. My answer will be just the number 3. That's the answer, option C. Remainder would be 3. Right? I hope that the approach is making sense. Right? Here's question number 10. Again a straightforward one. What happens when this expression is divided by 12? This should be easy to calculate. Yeah, you just have 3 numbers. You want the remainder when they are divided by 12, right? In fact, you can see that the numbers are also quite close to each other. Yeah. So, in fact, you could say 1423 is 1421 plus 2, and 1425 is 1423 plus 2, which means remainder of 1423 will be remainder of 1421 plus 2. Right? So, let's just divide 1421 by 12. 12 ones are 12, 22, 12, 221 rather. 12 ones are 12 again, but now I'm left with 10, 101. 12 eights are 96. I get the remainder as 5. So the first value will give me a remainder of 5, which means the second value will give me a remainder of 7. And so the third value will give me a remainder of 7 plus 2, 9. So you'll get the remainder as 5 into 7 into 9, clearly more than 12, which means you again want the remainder of this product, right? So let me do one thing. Why not divide separately and then calculate remainder? What about if I write this as 5 into 63? Then I can break this down into remainder of 5 into remainder of 63. I know the remainder of 5 is the number 5 itself, but when you divide 63 by 12, you'll get the remainder as 12 5s are 60, remainder is 3. And 5 into 3 is 15. So since 15 exceeds 12, you'll calculate its remainder again. Remainder of 15 when divided by 12 is 3. So the answer is option C. Spot on, Shaurya. Okay, here's question number 11. What is the remainder when 4 power 96 is divided by 6? Let me give you a minute to quickly solve this question. right? 4 power 96, right? How do I deal with it? So we want remainder of 4 raised to the power 96, right? There's no point in writing this as remainder of 4 whole to the power 96 because remember you're dividing it by 6. So what's the point? It's not 1 less than the remainder. And if you divide, indeed you'll get back to 4, right? So there's no point to it. So instead of writing it this way, you can write this as 4 square, for example, is 16. You can write this as 16 to the power 48, right? Maybe you could even write this as 4 cube is 64 raised to the power, right? 4 cube, 3 into 32, right? You could even write this as 64 to the power 32. It doesn't matter which route you take. 64 to the power 32 will be slightly simpler because if you divide 64 by 6, you would come back to 4, right? So this reduces to 4 to the power 32 and reduces the complexity. Then you again divide, 4 power 32, you'll again write this some ways, right? You can write this, for example, as 16 to the power 16, right? And if you divide this by 6 2s are 12, comes back to 4. So this becomes 4 power 16. Again, exceeds 6, so you must divide it again by 6. But 4 power 16 can be written as 16 to the power 8, which means again it becomes 4 power 8. 4 power 8 can be written as 16 to the power 4, again becomes 4 power 4. And 4 power 4 is in fact 256. So basically you end up with remainder of 256. When you are dividing it by 6, it turns out that the answer is still 4, right? So here you go, option D, it should be 4. Now this is one method. I deliberately showed you a longish method because there is another thing you could do, right? If you check it out, this is 4 power 96, base is even, and 6 base is again even. So why not? Why not write this as 4 into 4 power 95 divided by 2 into 3, and why not knock off the 2, right? Can I do that? Can I then divide 2 into 4 power 95? Can I calculate its remainder when divided by 3? Does that help me? Well, it turns out yes it does, right? Because let me first explain how to calculate the remainder. So we want the remainder of 2 into 4 power 95, but we're not dividing it by 6, we're dividing it by 3. So split this up, this becomes remainder of 2 into remainder of 4 whole raised to the power 95, right? And now you can see the big advantage kicking in. This remains 2, but remainder of 4 is 1, so this becomes 1 power 95, which is the digit 2 itself, right? But the last number that you get won't be the answer, because remember, you're getting the remainder when you're dividing a number with 3. So what would be the remainder when you're dividing the original number with 6? Remember, we cancelled out 2, right, in both numerator and denominator. So in the end, you'll say the actual remainder would actually be, take this remainder 2 and multiply it with what you cancelled out, right? Take the original remainder and multiply it with whatever got cancelled out. So answer will still remain 4, right? So just keep that in mind, that if sometimes you notice there is something in common between the dividend and the divisor, you can cancel it out, calculate the remainder with the remaining divisor, but then don't forget to multiply it in the end. Multiply it with whatever got cancelled out. Okay, here's another question. What is the remainder when 2 power 256 is divided by 17? Okay, let me check it out. Here's 2 power 256, right? And you're trying to calculate its remainder with 17. Now the trick is to know that obviously I'm going to try and write this, change the base, right? And the convenient base I'm going to choose here is that I'm going to write this as 2 power 4 into 64, right? Why do I choose 4? Because 2 power 4 will then be 16, right? And why is 16 good enough? Why is 16 a useful base? Because 16 is 1 less than 17, right? And so see what happens. If I write this as 16 power 64, then this will become remainder of 16 whole raised to the power 64. What is the remainder of 16? Well, it's 16 itself, but then I can also write this as 17 minus 1, right? I can also write this as the remainder of 16, which will be 17 less 1, right? What is the remainder of 17? 0. What is the remainder of 1? 1. So this becomes minus 1 to the power 64, which in fact will be plus 1. So the answer is plus 1, option A. That's a good answer, Shaurya. Here's another one for your practice. What's the remainder when 7 power 84 is divided by 342? Oh, 342. Yeah, this one is easier, right? Because 7 cube is 343. So I'll write this as 7 power 3 into 28, which means this will become remainder of 343 whole to the power of 28. And 343 remainder would be 1. So 1 power 28 is 1. Option B is the answer. Good answer. Okay, try this one out. Alright, you're marking B. Check it out. 6 power 500, right? 6 cube is 216, right? That's the hint. So then you can write this as 6 power 500 becomes 6 square to the power, okay, 6 cube, sorry, to the power 166. Right? Let me rewrite this actually. Right? 6 power 500 can be written as 6 to the power 3 into 166 plus 2, right? Which means this becomes, you can split this, right? 6 to the power 3 into 166 into 6 square, right? So this basically becomes 216 to the power 166 into 36. right? So if you want the remainder of 6 power 500, that will become remainder of 36 into remainder of 216, and this remainder must be raised to the power of 166. Right? What is the remainder when you divide 36 by 215? Remainder will remain 36. What is the remainder when you divide 216 by 215? Remainder will be 1. So 1 power 166 is indeed 1. So my answer becomes 36 into 1. That's 36, or option C. Careful, my man. In your hurry, I think you made a silly mistake here. Right? Okay, I think last question and then we'll break for the day. I think remainder should be fairly clear to you now. Right? Tell me what's the answer to this one. Seems to be giving you some trouble. Well, let's try and do this together then. We want remainder of 4 power 75. I'm going to write this as, I'm going to write this as 4 power 75 can be written as 4 to the power 3 into 25, right? So that's 4 cube, which is 64 to the power 25. So let's start with that. I'm going to write this as remainder of 64 whole raised to the power of 25. What is the remainder when you divide 64 by 11? 11 5s are 55. This becomes 9, right? So then I'm, 9 to the power 25. So I'm going to write this as 9 whole to the power 25. Yeah. Right? Or better still, I can also write 64. So in one step you're thinking 11 5s are 55 plus 9. But to make life simple, because you want this number to be low, you can also write this as 11 times 6 minus 2. 66 minus 2 is also 64. So I would prefer to write this as, minus 2 to the power 25, which would then translate into, obviously it's going to be a negative value. So negative of 2 power 25, but then I can write this as 2 power 5 raised to the power 5, right? Because then this becomes minus of 32 to the power 5, right? Now, this can be written as, you want the remainder of, so negative of remainder of 32 whole to the power of 5. Now what is the remainder of 32 when you're dividing it by 11? Again, think about it. 32 is actually 11 into 2 plus 10, but you can also write this as 11 into 3 minus 1. It's 1 less than a multiple of 11, right? So you can write this as minus of minus 1 to the power 5. Yeah? And there you go, job done. Minus 1 to the power 5 will be minus 1, and minus of minus 1 will be plus 1. So what's the remainder? Option B, answer is 1. Right? I hope that made sense to you, Shaurya, and anybody else watching. That's how you deal with remainders. Most of the time you can add, subtract, multiply, but sometimes you can also do these kind of manipulations by making them negative, right? Sometimes that's actually quite of value, right? Okay, on that note, I'm gonna bring this session to an end. Talk about 3 distinct advantages of the Unacademy app. One being flexibility in terms of choice of batches, in terms of schedules, in terms of language that you choose, even in terms of device or time of preparation, right? So plenty of flexibility all around on the app. Number 2 is that it's highly interactive, right? You can basically, if you want to interact with educators, high quality educators at that, Unacademy app is where you can do that. You can get all your doubts cleared live. Take a photograph, send it across to the educator, and he clears it up live in class, and can also answer polls that the Unacademy educator creates, right? And last but not the least is the ability to practice, because what you learn is useless if you don't practice, and Unacademy gives you plenty of tests and quizzes along with detailed reports and performance analysis, and also notes, right, that you can download in the form of PDFs, right? So plenty of learning material, all of it at your fingertips if you just subscribe to one of these subscription plans, right? Like I said, choose one of the longer term plans, and remember to use my referral code AV01 if you want a 10% discount, right? Well, if you like the session, do like, share and subscribe this video. Join me tomorrow again at 7:30. I'm going to continue discussing some important topics for the GMAT. Tomorrow we'll look at algebra. Yeah, so do join me at